Okay, it's 10 till, so if everyone's ready on that end, we'll begin. I'm very pleased to introduce Bernhard Haeupler tonight. He's well known to many of you for his impressive work in distributed algorithms. For those of you who don't know him, he got his PhD from MIT. He's currently a professor at Carnegie Mellon. He's on sabbatical at ETH and has done all sorts of impressive things. One of the things I love about Bernhard's work is how he brings tools from many different areas of algorithms and theory and uses them to design better, more efficient distributed algorithms. For example, he's played a key role in bringing techniques from coding theory to our community. Another thing I really like about his work is he often finds sort of elegant approaches that lead to sort of beautiful and simple algorithms. I think one of his best known papers from a little while back was his work on a simple analysis of network coding, which I think is really beautiful. On a more personal note, I always enjoy talking to him. I always enjoy talking to Bernhard, in part because of his seemingly relentless optimism. You know, me, I tend to be an algorithmic pessimist. I'm always convinced that whatever algorithm I'm working on is broken. It's not going to work. Talking to Bernhard, by contrast, he's always excited by whatever it is we're talking about. He's always sure something neat is going to turn up. So I'm super excited to hear his talk tonight. And I'm super excited to hear about this quest he's been on for universally optimal distributed algorithms. Bernhard, I'll hand it over to you.
Thank you, Seth. That was very, very kind of you. I'm super honored and excited to be here. This is my scientific home. Like, there's so many friends in the audience. I want to start a little bit different. I'm super excited to talk about technical stuff, but I think I'm just going to take like 15-ish minutes of this keynote to talk about something that also I think is really, really, really important to our community and society and academia and our institutions in general. And I want to start with coming out and just being public about I have ADHD, I have dyslexia. I've had to hide this for most of my life as long as I know. And I'm very happy to say that I'm done with it. And I want to talk just a tiny little bit about it because I think it's important. So why am I coming out? Why do I think it's important? Well, maybe why am I coming out now? Because I can. Because at this point in my life, neither my scientific career nor my livelihood is really gonna suffer from this, and it takes a little bit to like jump over the hoops, but there's not much to lose. And I think it's really, really important. And so that's why and why now. And why do I think it's important? Because there is a tremendous amount of stigma, misinformation, and lack of awareness, anything that surrounds neurodifferences. And that leads to, you know, a whole bad cycle of really bad things. So there's total lack of visibility. I know many colleagues. There's plenty of them that are different. I don't know anybody who is like openly autistic, openly ADHD, openly dyslexic. There's no representation. If you don't know anybody who is, there's generally a lack of awareness. It's really hard to self-advocate. There's a lot of involuntary discrimination and exclusion that just happen. There's also, when something comes out, there's also active discrimination. With the stigma, nobody wants to diagnose. Nobody gets diagnosed until things are really, really broken. People that could really be helped with treatment could be helped by just knowing what's going on, are not getting it. And then also the fact that all of this is hidden means that there's going to be, you know, stigma is not going to go away. The misinformation is not going to go away. And so all of this is like really kind of cycling around. And just to give you like a little bit of, so I prefer the term neurodiversity. So what does this mean? Just to give you a little bit of, what do I mean with misinformation? So neurodiversity is the best that if I had to like define it, it incorporates all kind of neurodifferences from like autism spectrum disorder to ADHD, attention deficit disorder, dyslexia, dyspraxia, OCD, Tourette's, all these like great medical terms for you know, diagnosing what's wrong with us. And if you look at it, attention deficit disorder is a horrible name because it has absolutely nothing to do with having a deficit of attention. If at all, I have too much attention, There's a lot of focus on things that there's, if at all, there's maybe it's harder to direct the attention maybe once. There's a little bit less control over where the attention goes. There definitely is not any lack of attention or deficit. Also, I think thinking of these things as disorders is just really, really bad. Like there's nothing broken with me. There's nothing wrong. There's nothing wrong with somebody who is like a colleague who's autistic. They're different. And different in genetic ways, in the wiring of the brain, in the brain chemistry, in the ways that we process emotions, in think, in the ways that we do things, but different and definitely not broken in many ways. And so, like, what's a different word for different? Exceptional, and I think that's also like that's really maybe a much better picture that you should think of, right? So think of it as like neurowirings and like thinking patterns on like the outer ends of the bell curve. And it's exceptional sounds a whole lot nicer. And generally, this is like way more common than you think, right? So depending on the cutoff, depending on which of these disorders you include, it's at least 1 in 10 general population. And we're surrounded by people who do amazing things with their brains, who are exceptional in many ways. There's not going to be fewer of those among us. That's just, and I think to some extent we know, but to another extent is that's on an abstract level. As I said, I don't know anybody who openly is different in any of these ways, right? So how does this look like in practice? Generally, exceptional means, you can be exceptionally good or bad or just, you're different. It just means that your, neurological profile is different. It's spiky if you compare it to normal, but maybe if you compare them among each other, maybe not that much. But and really, that's not just a bad thing. It's just different, right? So I wouldn't be here without my ADHD and dyslexia. Like I'm here because of it, not despite of it. Like it makes me like a really intuitive, creative problem solver. Like out of the box thinking, entrepreneurism are all like really tightly tied to dyslexia, also to ADHD. Like a storytelling brain, I can't memorize stuff, but I can remember stories. I can remember things. I can probably explain, like I can only understand simple things. So when I explain things, they have to be sufficiently simple. I think in many ways, it makes me a good advisor. Hyper-focusing on things. I can think about problems for 8 hours until everybody drops dead, and I didn't even realize that time passed. All of these things are really, generally, if you have a neurodiversity, chances are, you're thinking differently and you will find solutions that other people cannot, and generally that will make you a better scientist. And certainly in mathematics and in other places where it's mostly like a mental thing, you are predestined to be like a better scientist. But then, of course, also, there are other things. Generally, ADHD, for example, comes with, with different executive functioning compared to normal. So much less control, what my brain focuses on, time blindness, and comparison to other people, emotional regulation. For me, that's really a feature, not a bug. I love it. But if you constantly start crying, for other, that can be a problem. I like it. Being self-aware of what you're doing, having self-control, starting tasks, completing them, like at some point, it's already clear how it's going to end. My brain is like, I'm done with this. Let's go to the next thing. Not always great. And so generally that means, like notions of reliability in the normal sense are hard, being like fully professional, even though as a professor, as far away from being a real professional in some sense than you can be, and like living an orderly and normal life. Those things can be really hard, which again, not sure if that's a bug or a feature, but it can definitely make like a lot of problems, right? And they're just, if you think about what this means statistically, right? It's really bad because you're just not matched to your environment, or the environment doesn't match you. So unemployment can be as high as 70%. These are people that have tremendous abilities and just can't find employment, right? 3 times higher suicide rate. So when I read it, 13 years of lower life expectancy. And that's not because of the medical issues. That's because of your environment. Like, if you don't fit into the environment, you're gonna develop anxiety. If you can't be efficient, you're gonna develop like depression. If the world is not built to you, you're gonna have a higher number of accidents. If you're on the lower socioeconomic scale, you're gonna be a victim for violence, you're gonna have access to less health care, et cetera, et cetera. That's where this lower life expectancy comes from. It does not come from any, like, it's not a medical thing, it's a societal thing. And even for me, you know, like, statistically speaking, I shouldn't be here. I was schooled in a year late. I shouldn't have gone to a school that allows me to go to university. I really just wanted to get away from the bullies. Didn't really work. I, you know, failed the class. I had really bad grades. I basically was almost a high school dropout. I graduated high school age 21, right? From 6 to 16, like a decade of my life being different. It's not great. Kids don't like it. And, you know, I was like really severely bullied physically, psychologically. That didn't break me is really a miracle, and to some extent probably, you know, just thanks to my awesome family. But, you know, so many times epsilon far away from never learning any math, from not being here, from never knowing what my brain can do, from just thinking I'm completely stupid and useless. And, you know, like, add to that, you know, I'm a white, tall dude born in Germany, right? Add any kind of other thing to it, like give me a darker skin color, different last name, let me not be born in Germany, like less awesome parents, you know, make me a woman, like I wouldn't be here. It's already like just pure luck that I'm here. And that's a problem. Okay, this is kind of general, like there's many things that need to be changed, schooling and so on and so forth. But, you know, we in academia, we're like in our own small little bubbles. How does this look here, right? I mean, like, sure, all of these unemployed people, they, you know, many of them don't make it, which is a problem, but what can we do about that? But even at work, right? So information stigma is still there. You cannot disclose at work because you're gonna get actively discriminated against. And that's one of the points that people have a really hard time believing and don't see because you don't see it. But there's a reason why nobody comes out. There's, you know, hiding and, you know, not saying things is extremely taxing. And still, like, we all struggle in silence and alone. And there's a reason for that, because if you don't, it just gets worse. In the States, there's a big push for like diversity, equity, inclusion, which is great. There are many, many important things. But then even if you look in these, like, people are just not aware. You don't find yourself in there. It's not the most important difference in the world, right? But it is, and just people are not aware. And you know, without people having theirs that say, I have this, I'm proud of it. Here are things that are different. Like, can we talk differently? You know, like, without students seeing that, you know, this person has the same problem. I'm not just stupid. Like, I can make it to be a professor or whatever I want to be. Like, helping each other, informing each other, informing others. All of this is just not there. And I don't have easy solutions, but, you know, step by step, we really should change this. We should, and overall, this is like a big social issue, but it's also a big economical issue, because the people that are really predestined to do and make changes and be innovative often don't even get to do that. And the people that do constantly have to try to hide and kind of adjust and do it. And in the end, I spend way more of my energy on doing, you know, hiding and doing the things in a way that is really not efficient for me. And it really takes away from the things that I can do well. So thanks for listening to that. Let's, you know, here's a few suggestions that I have to change things. Like, most important thing, we have to learn about these things, right? So we have to rethink disabilities. We have to, like, understand that people communicate, think, feel, operate, work differently. You know, just Google, like, take 10 minutes, Google neurodiversity. Google is a social model of disability. Like, it will make you a better colleague, friend, teacher, everything. you know, once you know, like I think there's lots of people out there that want to make the world a better place, to make sure everybody can function, learn, grow. We need to, in some form or way, try to like get the stigma down, have an environment where any kind of differences like are celebrated or feel welcome, bringing them in a university. Like the more diverse we are, the more different viewpoints we have, you know, the better it's going to be. Yet if I look at my department, or, you know, it's all white, old black dudes, white, old, anyway, you got the point. And then, you know, also like give people different, like, what does it mean to be a professor, a good professor? There's a lot of like different things that that come in, or like a good worker, or a good whatever it is. It doesn't have to be. There's many different ways in which we can contribute, and they're not, you know, like give the system enough structure to let everybody find their own way to contribute, and you know, things are gonna be a bit better. Got through that. Thank you. Good. Now let's. Oh, what did I do? Yes. Okay. Now I'm gonna, yeah, come back to the part that I was actually invited for, I suppose, and let's talk some distributed algorithms and math and all that fun stuff. So in the technical part, what I want to talk about is kind of a general project or whatever that many other people, like Mohsen in particular, Goran, who talked at ADGA, you know, my students, Alice, Jason, also, you know, anybody like Christoph and Vasek, Harald Rekitasuke, like all of, like many people worked on it. I'm really bad at like remembering name and giving credit. When I say we, it's we as a community. You know, who cares? And that has really kind of come more or less full circle, and so there's a lot of things to talk. I'll try to give a high level intuition of a lot of things, but it's kind of a nice overall picture, so the time for this is like really perfect. Quick motivation, I don't think I really have to do this here, but just so why do I do distributed algorithms? Well, the you know, data is getting bigger. We can't even hope to store things on a single disk or do it process it with a single processor. So there's going to be lots of like the systems currently and all future systems are necessarily just going to be massively parallel and distributed. And so in particular, I want to look at graph algorithms. So then I think of this kind of two settings. Either I have a network like Amazon with like billions of servers that kind of need to want to compute and want to talk to each other, or also I have just an abstract graph like the Facebook graph, and I want to analyze it. And still if I create algorithms for it, I could do any kind of algorithms, but the algorithms that people run are necessarily going to look at nodes as entities and going to like send things around, are going to be message passing. And so generally the topic of communication over short and low congestion paths is like pretty universal in this kind of graph processing, or even just real network setting, right? And so we have this standard message, standard model, and in some sense we studied these things like way before they even existed or were relevant, and I think that's also the reason why now there's like a big push to come back to these models. So standard message passing models, you know, processes, undirected graph. We have some weights on them depending on what problem we want to solve. We can only send small number of bits. And now suppose, so the problems that I'm going to look at in this talk are global problems like minimum spanning tree, shortest path, min cut. Like take your favorite optimization problem from your undergraduate class. And now we want to solve it on a more in the modern world. We want to solve it in a message passing setting. And for all of these problems, at least, it's clear that you need at least diameter time. But generally, diameters are really small, right? I mean, diameter of the Facebook graph, I think average distance is like 4.7, maximum distance is like I don't know, 10, 11, generally network diameters, number of nodes, in the billions. So for me, in this talk, I'm not even gonna really talk about what factors I ignore. Generally, I think of diameters polylogarithmic, but also I'm happy to ignore like subpolynomial factors for now. Just, polynomial is large, subpolynomial is small. Many things I ignore polylog factors, which are, are really small. So we want to solve these problems. And then ideally, because it's the dream goal would be to solve them first order of magnitude, like in order d time, like with ignoring some polylogs or some polynomial factors, right? Because all of this is small. So I'm going to browse through this fairly quickly because I assume most of you kind of have seen this to this, right? So it's the simplest problem that kind of captures a lot of these things, minimum spanning tree problem. If you try to solve this in a parallel way, what would you do? Well, you do Borofka, right? So every node starts as its own component. Cheapest edge out needs to be in the spanning tree. Let's mark it to be in the spanning tree. Then, I get something like this. Might not be the full spanning tree. I might get some connected components. Each connected component, again, looks cheapest edge out, needs to be in the spanning tree. I put it in after login number of rounds, I'm done, right? So now, how long does it take to do one iteration? What I really want to do in the iteration is just, I have some connected component. I want to find the cheapest edge that goes out. Most trivial way is just flooding things around the component until, everybody's heard from the cheapest thing, which takes diameter rounds, and I'm done, right? Beautiful d log n algorithm, and that seems almost like correct, but it's not quite. So, I mean, many of you know why this is not correct, but who can help me out? Why is this not actually a d log n distributed algorithm? We am cheating just a time. Yeah. Yeah, so those I can do in diameter time, right? Yeah, so I'm cheating a bit here, right? So there's two different diameters. One is the graph diameter and one is the diameter of the components, right? And these two things do not necessarily have anything to do with each other. It's perfectly fine that there's like really long and windy components, where the diameter of a subgraph can be much, much larger than the network diameter, right? And really, we're running in diameter of the components. The best bounds that I know on like the diameter of component is n. So this gives us an n log n algorithm, which is not quite what we wanted. Good. So let's quickly browse through kind of what do we know as a community about distributed MST. Well, if you start with just straightforward implementation of Borofka, you get n log n, right? We saw this. If you do it a bit cleverer, you get n, and to some extent, you're done because this is optimal. But not really in a satisfactory way, right? So would be a short talk otherwise. So let's be a bit more precise what we mean with this optimal. It's existentially optimal in n, right? So there exists a graph on n nodes. In fact, for every n, there exists a graph on n nodes where at least omega of n runs is needed, and this graph is simply the cycle. If you want to compute the MST on a cycle, you need to drop it as the cheapest edge, and that's going to take like order n time. Okay, good. So maybe n is not really a good parameterization here, right? Because an order n algorithm on a Facebook graph, I don't know. Good. So then, 93, that's like whatever, 25-ish years ago. And then 95, Kuttin-Pelik, Gary Kuttin-Pelik, and then Kuttin-Pelik came up with this like really neat like square root of n plus d algorithm, which really started this whole area of like distributed graph algorithms. And to some sense, again, like this algorithm is optimal. But maybe again, we should be like a little bit more precise in which sense this is optimal for like any n and d, at least d not too small, like logarithmic. There exists a network in which at least square root of n rounds are needed, right? Good. I still wouldn't want to run a square root of n algorithm on a billion node graph. But good. So and more or less, so if we ignore the work in this direction, the state of the art is like many beautiful algorithmic ideas that give us these kind of optimal, existentially optimal in N and D algorithms and like lots of really important like ideas and understanding of problems is being generated for min-cut, exact approximate min-cut, shortest path, flows, Laplacian solvers, like you name it, right? And again, these are optimal in the sense that exists kind of a pathological topology on which no algorithm can do better. But then maybe again, the question is, does this apply to like the real world? Like if I have the Facebook graph, should I really expect that computing an MST takes like square root of the node number of times, roughly, right? Are there networks for which we can do better? Is there a model that we can like formally prove things about? You know, are there parameterizations? Is a different graph parameter that's better than maybe N and D? And I wrote I because I don't want to put words into other people. Like, I'm not sure if everybody agrees, but generally I think really for any networks that exists that we ever really care about, there should be polylog algorithm, like, or at least subpolynomial algorithm, like exponentially faster algorithms for anything that we really care about should be possible. And then the question is, can we like prove this? Can we make this formal in some formal way? And not the first one to ask the question. In fact, to some extent, this question like started with the whole area, like was already brought up in the very beginning by Gary Kuttenpelig, 93, which asked, is there a graph parameter that determines the distributed complexity of MST? And in some sense, the answer is yes. You could just say like opt MST, like the graph parameter is like the running time of the fastest MST algorithm on G, which is a well-defined function, but it's not particularly interesting. So probably what we mean is like, is a good approximation, like a nice description of this optimal running time of G, independent, like optimal running time of the best MST algorithm on a topology G, right? And then if you have this, then the question is, can we get these magical universally optimal distributed algorithms which match this graph parameter, right? Which are as fast as possible on every single topology, up to, again, some fudge factors, right? So different version of this question is a single uniform MST algorithm which doesn't know the network at all, but when you run it, it's gonna run in opt MST of G time, right? Is there an MST algorithm that can perfectly adjust to any topologies that you give it? Is there an algorithm that compete with the best algorithm that's out there, even if this algorithm is specifically designed for this topology, but my algorithm doesn't get to know it? Right? That would be like a really kind of cool and powerful thing, and this is exactly kind of what we're working towards. I don't think we ever really believed it's like fully provable, but that's what we ended up. In fact, I think I gave like an ADGA talk 2014, a Sirocco keynote, and like half of the slides are like from that keynote, like very convenient. And I just like, it seems that now it's like provably like we know that in many ways, like all the first part is still the same. So so here's what we know. This is all kind of under the framework of low congestion shortcut framework. You'll see in a bit why. So here's roughly kind of what we know. There's a large number of fundamental like distributed problems, MST, connectivity, cuts, flow, like all of the problems that are listed that have up to fudge factors the same complexity on every single graph. Right, it could be that like shortest path is completely like shortest path is easy on some graphs on which MST is hard, and vice versa. Like there's no reason a priori while there should be kind of a complexity class in which everything behaves the same. But many of these global optimizations problems, it just have the up to fudge factors the exact same optimal it's the same function as a dependency of G. And the reason really is that all of these algorithmic problems can be reduced to like very simple and natural communication problems. In fact, just I say route from here to here, here to here, here to here. What's the fastest you can do this? If your network supports something fast, it's going to have fast distributed algorithms. And there's two names for these problems. I will talk about them also a bit: partwise aggregation and multiple unicasts. They sound like complicated, but they're really like you'll see they're super natural communication problems. And then it turns out that if you make all of this rigorous, and you manage to get universally optimal algorithms for these communication problems for part-wise aggregation or multiple unicasts, then you also get universally optimal algorithms for all of these problems, right? So now, so this is what we get up to subpolynomial factors. And this part I'm not going to talk a whole lot about, but this is also nice ways to characterize or talk about this dependency on G. There's a lot of topological graph theory that goes into it, where say excluded minor graphs, planar graphs, bounded treewise graphs, or anything like this. All of these are nice graphs. Expander graphs, like many of the graph classes that we can mathematically nicely define. We can prove that they're nice in the sense. We can compute opt of G up to fudge factors. We have exact characterizations in terms of cuts, in terms of communication problems, in terms of many different things. Good. And that is already kind of nice, but what really kind of I think is nice that it turns out just asking that question and trying to work on it is actually equivalent and leads to many interesting results and many interesting questions in other fields of theoretical computer science, in other like scientific fields in general, which you wouldn't really expect any like connections, right? So it turns out that, and I hope to convince you of like show you some of this. So oblivious routing, like can I route without knowing what other things are there? Metric embeddings, is there a nice way to have compact routing tables? Network coding, which I happen to like do before that. It comes in here. Just happens to be the case. Online algorithms, approximation algorithms, different notion of expanders, expander decompositions. They really kind of all factor in here. In fact, many of the questions, yeah, you'll see that in a bit in general. And then to some extent, like if you do distributed algorithms, you're always caring about length of passes, and if you do congest, you also care about congestion. And so we have a long history of really thinking hard about how to do things in like fast in terms of dilation, in terms of length of passes, and with little congestion. And many of these metric embeddings or other fields are way older, but in these questions, we're really kind of ahead. And now combining these two things gives really kind of nice results in both directions. So generally, if you want to do general optimization and you want to jointly combine L1, shortest path, length of a path, sum of all path lengths, right? L infinity, cuts, flows, that we know how to do. If you want to jointly optimize things get really hard. And these are the problems that we have already been like thinking about quite hard for a long time. And so generally, the tools for universal optimality, they do solve big questions. We also get to like port things over into our world, and really it brings like many of these worlds much closer together. And at least for me, that's like very exciting. And in the end, also, I hope I get to this in the end, I think there's a very generic algorithmic framework that comes out of this, which says that in many ways, if you want to think about graph algorithms, independent of computation model like streaming, parallel algorithm, near linear time algorithms, distributed algorithms, there's a kind of a nice model that comes out of this, which kind of it's not just with respect to kind of distributed computing. So I'll give you a little bit of a, so I'll talk about part-wise aggregation and these communication problems just to show you what they are, so that because they're also super simple, and then try to like point you to some of these connections yeah. So here's the communication problem that's maybe closest to distributed computing, which is part-wise aggregation, which is basically exactly what we saw in MST, right? So part-wise aggregation is just I'm giving you part, I'm giving you connected components, they're no disjoint, and I want to just compute, and everybody has a value, I want to compute an aggregate. The sum, the minimum, the, whatever is six, one value of this counts the number of, any of these aggregates. And of course, as we saw before, the challenge is that the subgraphs the diameter can be large. And so I need to really use the whole network for communication. And it's clear that this kind of pops up in distributed computing because you do divide and conquer. You still want to run distributed algorithm on it, it better be connected. And if this distributed algorithm is as simple as it gets, basically just computing aggregate, then voila, right? That's where it comes from in MST. But it turns out that, all of the other problems that I said before, you can reduce them to just this kind of communication primitive. You can also think of this as doing computations on a minor, right? I mean, you contract it, and then you're just doing one round of congest on a minor. A node just aggregates. This is kind of a very natural communication problem. And there's a very natural kind of combinatorial structure. If you want to solve this part-wise aggregation problem, then clearly you cannot just communicate within a part, because a part might have really large diameter. So you need to use the network to do things. So now every part, I'm just going to give some edges that it can use. What do I want from these edges? I want that after I add the edges, diameter is short. Okay, but also I can't give an edge to too many different parts, because then I get congestion problems, right? If everybody uses one edge and there are many, many parts, you have a problem. So here's kind of, if you think about this for a second, this is the most natural kind of straightforward definition of what combinatorial structure you would want to solve these part-wise aggregation problems. Most and I call these like low congestion shortcuts. And it's also like very standard arguments that says that if I have a shortcut where I use each edge at most gamma often, like congestion often, and afterwards the diameter is at most d, then afterwards with some random delays, I can solve part-wise aggregation in gamma plus like congestion plus dilation up to polylogs. Okay, so really what we care about is I want something that minimizes both congestion and dilation, and I care about the sum or kind of the maximum of the two. And so this is shortcut quality, right? Again, like once you see it, it's like a super intuitive name if you don't know what, so this is shortcut quality, right? And this is like a nice kind of graph parameter, one nice way to define a graph parameter. There's actually, like if you come not from distributed computing, there's maybe a network communication problem, which is even more natural, which is multiple unicast. Sounds horribly, but it's just, I'm saying I have some packets that are generated in the networks that want to be sent somewhere else. I have an SI that wants to send a packet to TI, I have a S2 that wants to send to T2, and S3 that wants to send to T3, right? Happens every day on the internet, like you're sending packets to a specific node on the internet, just point-to-point communication, that's unicast, and we have many of them, multiple unicast, right? It's easy to see that these two problems are really kind of the same thing, right? If I have a path, like if my part is just a path, and instead of saying everybody should learn about the values, just the endpoint want to learn about values, yeah, that's like SITI, right? On the other hand, if I can solve the multiple unicast problem on kind of node disjoint connected things, then I can take this tree that spans my part, like the shortcut, do a heavy light decomposition, decompose it into kind of log n passes. And in each pass, I just do divide and conquer. I first send it from the starting point to the middle, and then from the middle, in parallel, so now node disjoint to the middle, and so on and so forth. So up to polylogarithmically many rounds, multiple unicast or part-wise aggregation, really the same thing. If I talk to anybody outside of distributed computing, I never really mention part-wise aggregation. But if you want a model that kind of, if you want a primitive that's kind of nice in a distributed sense, reduce things to part-wise aggregation, right? So it's a slightly more powerful, more convenient thing to do. And so you can also, so the optimal, right, so what are shortcuts for this multiple unicast thing? Right, now SITI and so on and so forth. Suppose that I have, for each SITI, a node disjoint long path. So there's a congestion one, if I have to throughput, if I just ask about throughput, I can follow these long passes. But now I'm saying I just want to send one packet each. And sending it along this long path takes really long. So now I'm asking you, for these long passes that are disjoint, can you find short passes that don't have a large congestion, that don't overlap too much? That's just the natural. And in fact, if I have short passes that don't overlap too much, then latent max-Rao or random delays, or then the overtime to complete this communication problem is just maximum length plus the maximum congestion up to polylogs. right? So I'm really asking, can you find me these for disjoint long passes? Can you find short low congestion passes? Or can you find me a min completion time? Can you complete this communication problem as fast as possible, right? And so shortcut quality is the same, or optimal PA, or all of this is the same as saying, I give you any communication problem where I have long node disjoint passes. Now ask you, how fast can you solve this, complete it when there's just a single packet? That's shortcut quality. That's the running time of MSTs. That's the running time of many optimization problems. Okay, good. So multiple unicast, part-wise aggregation, same problem, both supernatural, just purely communication problems. What do these have to do with all the things that I said before? Here's, the universal optimal MST algorithm I claim is, now just this. It's not, doesn't really look that much different. For log n rounds, I'm getting these, I'm running Borovka. I'm getting these connected components. They're problem specific. They grow kind of organically. I have no control over them. But then for these, I compute the lowest shortcut, or I compute the fastest multiple unicast communication problem. And I get the minimum. Once I have the minimum, I add it to the tree and I repeat it, right? And I claim this is I claimed, and now we proved that this is like a universally optimal MST algorithm. And the running time is, well, the optimal time to do part-wise aggregation plus the time that it takes to compute part-wise aggregation times a log, which we ignore, right? Good. So the claim is this is a universally optimal algorithm. What do we need to prove, and what does this have to do with anything else but distributed computing? So here's the general recipe, or the general kind of steps that one needs to do. Upper bound and lower bound. So the first thing is you need to reduce your problem to part-wise aggregation. This is problem specific. For MST, it's trivial, right? It just pops out naturally. For other problems, it's less trivial. This is where you really need to understand the problem, where we need to use all the works, like just algorithmic works. This is what one always still needs to do, right? I cannot, So, but then the second part is I still need to construct these, like the algorithm, MST algorithm had this like, let's now compute a fast shortcut, right? You still need to get an approximately optimal shortcut. In fact, you also want it fast, right? So these two steps, they are kind of part of any of these universal optimal algorithms. These are done, but there's kind of very interesting things that are happening here. On the lower bound part, what do I need to do to convince you that this is a universally optimal algorithm? Well, again, so the way that it typically works is we prove hardness for like one problem, let's say connectivity, and then we show that shortest path, or MST, is at least as hard as connectivity, right? And to some extent, this is already done by Dasama et al. Like you prove that square root of n hardness, and then you reduce from there, right? So this is typically easy. It's still problem specific, but it's typically like super easy. And then there's kind of two parts. One is I'm going to use shortcuts to solve this part-wise aggregation problem. Shortcuts, we're really just routing along things, but it's a communication problem. Communication, I could XOR things, I could do funky stuff, right? I'm claiming that this shortcut algorithm is the best that you can do. So at the very least, I'm implying that coding cannot help you significantly, right? This actually is like a network coding gap statement. We're saying coding cannot help you over routing. The other part is you also need to show that, shortcut, like the time to solve connectivity is at least as much as like this graph parameter, shortcut quality, or whatever. And what makes it a bit interesting here is usually we just pick like one nice graph and we bet our communication problem here. Right here, I'm saying like, I'm giving you an arbitrary graph. Can be anything. I want to, now you have no structure to work with. You still need to somehow find and embed your communication problem here. Warren talked a good bit about this. This part I go a little bit less into. Okay, so here's how it connects to like network coding. I already said, right? We're really asking, can coding help for multiple unicasts to complete it faster? Because we're claiming it does not. We're claiming we just route, and we claim now it's optimal. So better, coding doesn't help you much. And in fact, this is kind of, in some sense, related to like the biggest open problem in network information theory, which is called the multiple unicast conjecture, where the conjecture is that if you're talking about throughput, coding does not help you at all. Like not a constant, not even a constant factor, it just doesn't help you. It's a notoriously hard question. Say building a complexity theory around it turns to be equivalent to like circuit lower bounds and other things. It's a bit different in the sense that a log-in gap is fairly easy, just by sparsest cut. Like if you routing is basically just multi-commodity flow, fractional version, but rounding doesn't cost you a whole lot. And sparsest cut is just saying if I can cut k sources from each other by cutting only a small number of edges, then the time to get the information from here to here is at least kind of k over the number of sources divided by the number of edges that I cut. And for throughput, you know, this is up to a log n, this is tight, right? This is the classical multi-commodity min-cut flow gap. What we want is completion time, right? Not throughput. And that's a strictly harder problem because throughput is saying I have a large number of packets here. And once I find kind of a low congestion path, I can just pipeline them. So the length of the path at some point, if there's enough packets, doesn't matter, right? We're saying, what if there's just a small number of packets? What if I also need short passes? And much harder problem, easier in the sense that if we can say it doesn't help much, polylogs, subpolynomial factor, we're still happy, right? So it turns out that network coding can help. Statement like this for throughput would be like a breakthrough. So completion time is harder, but it cannot help too much. It can help at most a log square time. So this is the first kind of type of result for like completion time network coding gaps. It's super interesting in information theory. Most of you would like not want to think about this question necessarily, right? And in the end, you need to kind of think about what is the right version of a short hop sparsest cut. Like what is the right certificate that tells me that something has to take a long time to complete instead of just large throughput. And in fact, for this proof, like we really took over like the Dasama embedding of communication theory and like the moving cut equivalent, like the short hop or distributed equivalent of a sparsest cut is coming from distributed computing, but it's solving problems in information theory. Here's a kind of here's a fun little example. So generally, so this says coding doesn't help for distributed computing, at least not much, which is actually funny if you call it like bound complexities, which is in the sense that if you want to know how can it possibly help, there's two things to point to. There's this like really nice paper by Masharegi and King, which says that you can get significantly polynomially better MST algorithm in terms of message complexity if you XOR things together than if you just route or do comparison based. Maybe some of you have seen this work. Here's also a concrete example for a gap and things that like surprisingly things that you can do with information that really in the beginning maybe contradict what you think you can do. Like simple network, right? S1 sends to T1, S2 wants to send to T2, and so on and so forth. Black edges are 3, length of 3, blue edges that go over the special S and T node of length 1. Okay, so every node has like an S1 through S to T through T1 pass of length 3. But of course, they're all going through the same edge, right? So how fast can I complete this thing if I just do routing? Well, I really have to go through these black edges, and then there's at least a path of length 5. Or I can try to, everybody uses the like ST edge, and there's five guys, it can only send 1 packet at a time. It's gonna take at least 5 times, right? If you do coding, this is a faster solution. And if you've seen this before, then it maybe even jumps out at you. If you've not seen it before, it's like, how can it help you? So here's the coding solution. So we have, the graph, the black edges is basically like a complete bipartite graph, except for the matching. Right? So you can't send to the person that you want to send, but you can send to everybody else. So what can I do? In 3 rounds, I can send to everybody but the person that I want to send to my message. So everybody, like it's after 3 rounds, T2 over the black edges knows all the messages except the one that it's interested in, right? And that holds for T3 knows all the messages except the one that it's interested in. Now what I can send, everybody can also send to S, and over the ST edge, I can just send the XOR of all the messages. That's just log and bits. And we can send the XOR of all the messages to all the T nodes. Now every single T node has the XOR of all the messages, and it knows all the messages except the one that it wants. Voila, what do? We just XOR out all the messages, and I get the message that I want to have. And these are things that you can do with information like that you cannot do with routing, right? Like there's an apple banana, which you also have a banana, it becomes a full apple. And if you have an apple that becomes a full banana, it's not just half, it's like this weird mixture. It's not like a liquid, it's information, and you can do cool things with it, but not too cool things, which is good, because for as long as we ignore polylogs, we can pretend that routing is the best thing there is. Good. Other questions about this? I saw lots of people nodding. Does this make sense? Lots of smiles. That's a good sign. Awesome. Okay, here's another fun thing: oblivious routing. So we have this multiple unicast thing we want to send from S to T, right? In fact, we want it distributedly, so nodes don't know the network traffic. They don't know, maybe they know the topology, maybe not, but we want to do communication locally. And now, if you have a network in which there's a fast algorithm, let's say your low degree node, in polylogarithmic rounds, you need to be done. Over each of your edges, you receive only polylogarithmic bits over the whole time of the algorithm, right? So somehow, if I have a packet that I need to send through the network, I learn polylogarithmic bits, and then I need to figure out a path. And the demand, of course, like the other demands are going from here to here. I have no chance of learning who else wants to send to where. How does the network traffic look like? The demand is like n bits or n log n bits to specify. I can't learn this. I get almost zero information about the other demands. I still need to figure out how to route my packet without creating a lot of congestion, right? And that's not a full proof, but basically, if you learn nothing, then this is exactly oblivious routing. Oblivious routing says, can I ignore what the other demand pairs are there and choose a path for my packet and still be competitive with the optimal solution? Here we're saying you learn almost nothing, but let's pretend that you learn nothing. Then distributed multiple unicast is really asking, give me oblivious routing. And to some extent, we know oblivious routing, but we only know it for congestion. Like we know that if you have ST routes and you're asking for alternative routes, and I'm just giving you ST pairs, I can define a distribution over passes such that if you randomly sample from it, the congestion is at most a log n factor more than the optimum, no matter what the demand is. Mind-blowingly awesome result by, like, when I say V, in this case, Haltrecke. But this is only, congestion. The passes can be arbitrarily long, order n long. And in fact, completion time competitive, so short passes and low congestion, you can do for expanders, hypergraphs, and so on and so forth. It was listed as one of the 8 most important open problems in distributed computing. For which graphs can you do it? And generally, there was like a proof under some formalization that says for general graphs, it's just not possible. But it turns out that maybe that's not the right formalization, and in the best way that you can ask for, it is possible. And I don't think we would have ever gone there if we weren't inspired by kind of universal optimality in distributed computing. So right. So what we basically prove that there exist these distributions, very polylog competitive in congestion and dilation. Like the passes get at most a polylog longer, the congestion is at most a polylog more, but you can get completion time competitive oblivious routing. And if you know how kind of the normal routings work, so it goes through LPs and so on and so forth, and you use these tree embeddings. And what you need here is basically tree embeddings for hop constraint distances, which all the people didn't exist, where generally, if you have a metric, you can, up to log in distortion probabilistically, pretend that it's a tree. And you get million approximation algorithms. It's a super, super powerful thing. now we want to look at hop constraint distances. So I want to ask, I only allowed to go 10 steps, log-in steps, or whatever, diameter many steps. Is there a path that's so many hops? What's the shortest path? And that's not a metric, because just because there's like a 10 hop path from here to here, that's short, and a 10 hop path from here to here. Triangle equality would tell you, like in a matrix, there's also a 10 hop path from here to here. That's just not true. These things are very, very far from being a metric, but it turns out you can still do like probabilistic tree embeddings. There's like Goran, Ellis, and these things also give you many new polylogarithmic approximations for online algorithms, for Steiner trees, for like when we wrote the paper, there's not even a word about distributed computing in there, because I mean, this is something that we'll use also for distributed computing, but people care about kind of in general. And what you get out of this, if you put it all together, is you get these kind of oblivious routings as we want them, but only the existence. Right? So now, yeah, okay, now I think. Now you can go one step further, right? Existence of like nicely competitive, multiple, like oblivious routings is not quite good enough for us, right? Because we also need fast and distributed like ways of computing them. And if you go back to the kind of, right, actually one fun point is if you have a fast distributed algorithm, then this automatically also implies like compact routing tables. Compact routing tables is to say a preprocessor network, and I put like little information, like small amount of information into every node, and now I can route things competitively or like in some way. If you have a fast distributed algorithm, a node cannot learn terribly much in this time. It's fast and it's low number of edges, and so you just store whatever you learned, and that has to be enough to so automatically get like the existence of compact or oblivious routing tables, again, is kind of a much weaker method, like much weaker statements than distributed oblivious routing. And the only way that we know about the existence of oblivious routings tables, the only way is that we get even just near linear time algorithms, sequential, not even parallel, not distributed, for oblivious routing in the normal world is going through expanded decompositions. We're basically in expanders, we know how to do things. Random intermediate nodes, and it's here. It's all great. And if you want to do it for general graphs, you decompose your graph into expanders, you route internally, and then you again, you contract and you run again an expanded decomposition. You have these hierarchies, right? Now, if you want to do this in the distributed, like if you want to do this for here, the problem is that every time you contract and you now route in this contracted graph and you uncontract, then the diameter of these expanders like is going to increase your path length. And this expanded decomposition kicks out a 5 fraction of edges, but it also blows up your diameter by 1/5. And in the end, the passes are really, really long, right? So I can't go into, like, I know this is all like super fast and can't go, this is more teasers than anything, but in the end, what you need to do is you need to define a completely new class of short, we want expanders where you have short passes through it, right? And there's a completely new kind of object. You can develop like a really nice theory about it. And then also turns out that you can get an expanded decomposition, which still only cuts a 5 fraction of the edges, but has passes through it, oblivious passes and everything, that are h long, where h is much smaller than 1/5. And these expanded decompositions exist, these objects exist, and one can compute them fast and distributedly. We're still writing it up. Mosen and Hardrecke. It's going to be fully out in 4 weeks or whatever, I hope. But kind of that's one of the kind of, and I think these objects are also interesting, like very completely independent of distributed computing or universal optimality. It's kind of a nice little thing that came out of it as well. So perfect timing. Quick summary. So this whole thing that we have here is saying that all of many optimization problems, and I think there's more work to be done. I think if I really want to understand a distributed optimization problem, then I'm trying to put it into this class. I'm trying to see, can I solve it with part by segregations? For many problems, we know that that's the case. There's many more problems out there, and there's interesting work to be done. Like one really needs to understand the problem in a kind of new way, or like in good enough in order to be able to do this. We get these universally optimal algorithms, which are really kind of nice and powerful guarantee for how fast does it run. And in the end, we get lots of new tools that talk about short passes and low congestion passes. We talked about these tree embeddings for bounded distances, network coding gaps, oblivious routing, and so on and so forth. Also, that's more like a meta level thing, but I really think this is in many ways the right way to think about graph algorithms, independently of what model of computation you're looking at, right? So we're saying that if you have a graph problem, I can reduce it. We're not quite there, subpolynomial, but often I believe you should be able to reduce many graph problems to polylogarithmically many aggregations, polylogarithmically many ways in which you just look at a minor and you do one round of congest in a minor, or you aggregate in a minor. And if you can do this, then this will automatically give you, in many kind of computational models, will give you a nice result, right? I mean, you will get near linear time algorithm because aggregation is near linear time. You will get fast parallel algorithms. MPC, it's also interesting, except that we're losing polylogs that often then, you need to do things maybe a little bit tighter. Maybe LCA, semi-streaming, like it's such a powerful way of understanding a graph problem. We say all you need to do is polylogarithmic many amounts of like computing an aggregate in a minor. And this goes both ways, right? So in particular, I think what we can get out, like here's a few results that we think can get out of it. This is like ongoing work, which hopefully also is going to be out soon. Like even if I don't care about distributed algorithms at all, or if I want to use kind of methods from distributed computing on problems that are people outside of our community care, if I want near optimal parallel algorithms, so algorithms with M polylog work, polylog depths, right? Clearly important problem. Deterministic 1 plus epsilon shortest path, fundamental problem. We can get, we believe that we can get this out of just this framework, right? You automatically get it. You also then get distributed algorithms, but probably there's a wider audience that cares about like the best kind of deterministic 1 plus epsilon shortest path algorithms. Low stretch spanning trees. People don't know how to do it randomized. People don't know how to do it deterministically. These things are also like really important in many places. Thinking about distributed computing really gives us kind of new problems in this world. Various embedding, tree embeddings, again, so one embedding also for like coming from various different places, very different communities care about it. And to some extent, many of our square root of n plus d like algorithms are really just doing, reducing it to partwise aggregation and then using the trivial kind of shortcuts where for large parts you just flood and for everything else you give it away. More or less are just doing this. So there's a lot of like algorithmic works that's been done that has a way wider applicability than what was maybe intended to. And I think thinking about things in this way can be, can lead to a lot of kind of interesting interaction and results. So thank you.
Okay, thank you. So, any questions?
Questions? I know I power blazed through this a little bit, and couldn't quite decide what to not tell you.
I have a question. So I don't remember. Oh, can you guys hear me well?
Yeah, Andrea, it's perfect.
Yeah, okay. It said that the internet connection was unstable. So about practicality, how many of these algorithms would you say would be easy to implement in practice? Like, what would be your insights there?
I think the answer is the usual. where if you take any of these like theoretically like cutting edge algorithms and you implement them as they're written, with us not caring about log factors and constant factors here and just making them like easy to understand and kind of built upon mathematically, they will not perform well in practice. All the practice is way more messy, right? There's never like a very clean, clear problem that's just fitting this and has no extra structure. But I think, yeah, I mean, if you look at which algorithms are being used in practice, like even if they're just heuristic without like, actual provable guarantees, they're clearly inspired by the work that's coming out of this community, right? So to some extent, it's about understanding problems better. And if you just take it straightforward, yeah, it's likely not going to be practical. But does this have I mean, why do I care about like square root of n versus like subpolynomial? I really want to understand problems, but I also think that if it was square root of d, like I wouldn't care, right? D is small in practice. These square root of n algorithms are running in square root of n time on every network. They're not going to be faster on a practical network. We're literally saying like here, there, they have square root of n very much hard coded into. So I think the ideas are very, very practical. The actual algorithms, yeah, not.
That's exactly what I was wondering, like how it had bridged to practice. And I didn't mean like the exact same theoretically optimal algorithm, but like the main idea. So thanks.
Thank you.
So I'm curious, what do you think are the biggest open questions here? So there's a lot of results here, a lot of things that are sort of sounds like here almost done. What are the biggest open questions?
I don't know. Maybe it's really just the beginning, right? I mean, maybe just saying this is the right way to think about things. So there's a lot of cool things happening in optimization, right? With algorithms that look very different from like combinatorial things that we used to, like continuous optimization, multiplicative weights, and all of these things, which if we really, in the beginning, it's like, oh, this is math that I cannot do. And this is like, they're solving problems that I like and love faster than I can. And that's but in the end, they also end up being like very combinatorial problems in the very end. They're still talking about spanners and low-stress spanning trees, and it's just a different language. Multiplicative weights is a super combinatorial, like nice process. And so like bringing these worlds, I think the model, for example, of reducing to like minors, and we also like there's a nice paper, Bridget Pang, Warren Gramos, and others that observes this for Laplacian solvers, for example. Like thinking about minors and about graph algorithms in this way, I think can have influence in the optimization world, but it can also really bring powerful methods into distributed computing. Like the shortest path algorithms that I list here. You can think of it as continuous optimization, but I don't like it, but it's using the whole, it's doing the same thing, right? So I think there's a lot of, yeah, like a lot of things that we, can do, yeah, like bring modern kind of optimization techniques in there, bring ideas from distributed computing out, generally kind of look at the graph algorithm field as something that really has structural implications and like implications outside of what we used to. And I think there it's really just the beginning, right? Sure, universal optimal algorithms exist, right? Nice, but then I think that really suggests like a lot of things that are completely open, right?
You mentioned
Maybe
the
I have a
work
question.
of. Sorry.
I guess Shai, go ahead.
Thanks. You mentioned the work of King. I assume you're talking about her work on less than m messages, less than m number of edges messages in
KT1,
slightly, yeah, KT1. slightly different model. Do you think that this work could be applied there also?
I think generally, so if you care about message complexity, in fact, I think you really want to think about low congestion shortcuts, because it turns out that like at least order M message complexity you get for free. Also, if you want to think about de-randomization, you can do this for every problem separately and de-randomize our squared of n algorithms, or you can de-randomize shortcuts, and then in many cases you're, which is, you're done. For even KT0, right? So, okay, so for everybody who doesn't know this, if you talk about message complexity, how many messages do you send around? If you don't know anything about your neighbors, it's clear that you need at least order M messages. Like, if you assume that in the beginning you already know the IDs of your neighbors, then it turns out that with coding tricks, and if you have long amount of time, you can do this with order N messages by doing coding, right? Where if I connect a component, I XOR all the edges together, and the one where both endpoints are in are getting XORed twice. So they're actually falling out, and the edges that are only in my connected component once, they're leaving it. They're XORed once, they remain. Super powerful trick. Yes, if you think about KT0 and you want smaller than M number of messages, I'm not sure if it's even possible to do this fast, like in small number of rounds. But if it's possible, then in fact, you will automatically get it for shortcuts, because in the end, shortcuts, as long as I give you like a connected graph in which I can do this, I can now build shortcuts. In some ways, yeah. So I think there's a lot. It's super interesting question, yes, I think it totally makes sense to think about like sublinear and KT0 messages for shortcuts, and then that would imply things for many, for all of these optimization problems. I think that's a short answer. I'm happy to talk about this offline. It's just going to get very technical.
Thanks.
It's a great question.
Okay, I guess let me ask my question and then we go to the remote one. I guess with what you're doing here, you're using randomization in all places. So can we say something about universally optimal algorithms if they have to be deterministic?
Yeah, in fact, I don't think there's anything inherently. I mean, we had a paper which says that at least for like extruded minor graph, like it's the things where we had low congestion shortcuts before kind of for general graphs, we made things deterministic. These low congestion shortcuts, they use expander decompositions, HOP expanders, like there's a lot of new stuff. But generally we know, not for these specific expander decompositions, there's nothing inherent randomized in expander decompositions. I do believe that like you de-randomize HOP expander decompositions, then for most problems you already automatically get a deterministic algorithm. And in fact, like for this like deterministic shortest path in parallel, sure, the part where we use like part-wise aggregation in the distributed model, we don't know how to de-randomize it, but in the parallel model, deterministic part-wise aggregation is trivial in parallel, right? I mean, you just pointed jumping. And so, yeah, I think you get this, yeah, you get deterministic algorithms out of it. And many like getting the fastest deterministic parallel algorithm for shortest path, it's going through like part-wise aggregation. And I don't know any other way of doing that. So are we there yet? No. Also, like, can we reduce the subpolynomial time of expander routing, expander construction, all of these places to polylog? I think we should be. It's not necessarily an easy problem for de-randomizing expander decompositions. A couple of problems that I don't know how to solve yet, but I don't think there's anything really inherently deterministic in there. Yeah.
Thank you.
Also happy to like think about those questions if anyone is interested. Yeah. Well,
I have one question online. Hope you can hear me. Am I audible?
We can hear you. Yes. Good. Now
So I have a question on the basic model. If this is in the congest model, right? If we consider asynchronous system, how would it change? And if we consider shared memory system with failures, would any of the results, can they be translated to that word? Like one is distributed system.
Generally, I think there's some. I mean, these are like super fundamental questions. Can we transfer congest algorithms into like more asynchronous systems? And I think like spanners, like there's really early works and cool stuff that synchronizes spanners, right? Lots of things grow out of this that give some kind of general answers to this. Faults. Yeah, I mean, I'm not sure. Then one also needs to define models. Yeah, so then there's a good questions. I don't know if I can have anything intelligent to say about it without like starting to like hash out what exactly do we mean with faults, what exactly do we mean with like an asynchronous system.
Or it is shared memory system. If not asynchronous shared memory system?
I think I know too little about that to really, yeah. I would like to know more about it. I think I've one like shared memory paper with Philip, but in the end, they just translated it into a nice combinatorial problem that didn't have much of the shared memory thing in it. So I'm willing to learn, but I don't know much about it. So if somebody wants to teach me, please.
Maybe we can discuss offline.
Yes, thank you.
Thank you.
Okay, so thank you. I think we'll further discussion can happen offline on Zulip or during the break. But I think let's thank Bernhard for his talk, and then come back. Next session starts in like 15 minutes. So thank you, Bernhard.
Thank you.